Hello everybody, so today we are looking at 8.4 of the textbook at exploring and travelling problems. So this is basically looking at the Eulerian Trail and circuit and also the Hamilton Path and circuit. So there's two types of paths and circuits. So let's make a start about what is the difference between all these words: walk, a trail, a path, a circuit, a cycle. So basically we know that travelling involves going from point A to point B, but we might stop along a few points on the way, or we might take the scenic route. We're basically traveling one spot to another, or back to the beginning again if you want to go for a walk or something. Okay, so traveling and exploring a graph basically involves moving from one vertex, because vertex represent places, via an edge, and that's like your pathway, and is described by listing the vertices that are visited in that order. Okay, so a number of terms used when discussing traveling and exploring are listed, and we're going to go through those. So these letters are basically written in order from the vertex points that we're traveling through. So a walk is basically defined as a sequence of vertices of a graph along the edges. They could include repeated vertices or repeated edges. So I might be going like there, back there, back there, back that way, and like I can crisscross and stuff like that as well. Okay, so an example of a walk could very well be, all right, we start at A, we go to B, okay, from B we go to F, from F we go to H, from H we go to G, G we go to F, and then from F we're going to end our walk at B. Okay, so that's what we call a walk. The next one is what we call a trail. So a trail is basically a walk, but there's no repeated edges in it. Okay, so I could maybe start off at G. From G, I go to F. From F, we go to H, back to G, back to I, and then to J. Okay, so we can repeat a vertex, but we're not repeating an edge in that one. Okay, the next one that we look at is called a path. So a path is a walk, but there's no repeated vertices in this instance. So an example could be starting at B, we go to A, we go to D, we go to E, and then we end at C. Okay, so that could be a particular path in your network. All right, looking at a circuit now. So a circuit is basically a walk. There's no repeated edges. Okay, so it's similar to a trail, but it's going to start and finish at the same vertex. So say we start at the point G, we go to F, we can go to H, we can go to G again, we can go to, back one step. We can go from H to G to I, to J, and then back to G again. Okay, so that could be a circuit. And then the final one is a cycle. So a cycle is a walk, this time with no repeated vertices, and again it's going to start and finish at the same vertex. Okay, so if we start off at A, from A I go to B, we go to C, D, E, and A. Okay, so that is a cycle. So this terminology here is really important. I would be putting that into my bound reference of notes. All right, I'm just going to erase all of my scribbles that we made, and we'll go on to the next section. So a little hint for you as well, if there's no repeated vertices in a walk, then there's probably going to be no repeated edges. So this means that paths and cycles have no repeated edges and no repeated vertices. On to our first kind that we're going to look at is an Elorean Trail or circuit. So an Elorean Trail is basically a walk that's going to include every edge once, and it's going to start and finish at a different vertex. Okay, for an Eulerian trail to exist, the connected graph must have exactly two vertices of odd degrees. So remember, a degree of a vertex is, in this example, this vertex A, the degree is 1, 2, 3, or 4. So it's how many paths are leading away from that particular vertex, okay? To find an Eulerian trail, basically you have to start at one of the odd degree vertices and you finish at the other odd degree vertice. Okay, so there's 2 vertices that have an odd degree, so they're going to have a 1, a 3, a 5, a 7 pathway. It's going to start at one of them and end at the other one. An Eulerian circuit, however, is a walk that basically includes every edge once still, but this time we start and finish at a different at the same vertex. Okay, so Eulerian Trail is at different vertex and Eulerian circuit is at the same vertex. And for an Eulerian circuit to exist, it's going to exist if all vertices are of an even degree. Okay, so this is sort of like your formula for how you know if these things are going to exist or not, if you're able to draw them. If we look here, an example of this network has exactly 2 vertices with odd degrees. So F, okay, has 1, 2, 3, and I also has 1, 2, 3 as its degree. So most likely, if we're creating these, we're going to be starting off at F and finishing at I. Okay, for a trail at a circuit, it might be slightly different. In this case, because we do have odd degree vertices, an Eulerian circuit is actually not going to exist. So when we're doing Eulerian stuff, I would always look at the degrees of the vertices to see if a trail or a circuit is even possible. The 7 bridges problem that we've seen quite a few times is probably a really good example as to whether we can say, oh, can we cross all of like the sides of the bridges without crossing parts again? Do these Eulerian trails exist? So redrawing this sort of diagram as a graph, you can see how many degrees each vertex is going to have, and we can see that all 4 vertices have odd degrees. Okay, so if they all have odd degrees, an Eulerian trail is not going to exist, okay, because for an Eulerian trail to exist, there only has to be 2 of an odd degree. So it's basically impossible to complete the walk in a way that crosses each bridge only once. And you can try starting at 1 and see if you can figure it out. You won't be able to for this one. All right, Hamiltonian path and cycles. So a Hamiltonian path is basically this time a walk that includes every vertex only once, okay, and it starts and finishes at a different vertice, okay. A Hamilton circuit, on the other hand, still includes every vertex once, and this time starts and finishes at the same vertex, okay. So where Eulerian circuits are looking at the number of edges, okay, we're crossing the edges once. So the way that I remember it is Eulerian starts with E, edges start with E, so that's our focal point. With Hamiltonian, we're focusing on passing through every vertex only once, okay? And whether it's a path, it's going to be starting and finishing at different vertices. If it's a cycle, we want to aim to finish and start at the same vertex. So unlike Eulerian trails and circuits, to determine the Hamiltonian path existence, it's basically trial and error. You've just got to be like, oh, is there a path that exists? So in saying that, let's go through a couple examples. So looking at worked example number 8, we basically want to see for this graph here, determine whether any of these things exist. So we've got to start off by looking at an Eulerian trail. So let's have a look and see how many vertices actually have odd degrees. So A has 2, so that's even. B has 1, 2, 3, 4, that's even. E has 1, 2, even. H 1, 2, 3, ooh. J 1, 2, I 1, 2, 3, ooh. F 1, 2, 3, 4, C 1, 2, D 1, 2, 3, 4, G 1, 2. So it has 2 vertices with an odd degree. Okay, so this means that an Eulerian trail will exist. Okay, and we can now figure that out. So there's other examples, and there's many examples of which Eulerian trails can exist. But remember, for an Eulerian trail to exist, it's going to start at 1 odd degree, and it has to cross every edge once, okay, to figure this out. So to do this, we could maybe start off at H. Let's test it. We can go from H to E. Let's go H to B, to A, to D, to C, to B, to F, to D, and then we can maybe go down to G. let's go to I, F, H, J, and I. So I started here and I finished here. So in this instance, that is the Elorean Trail. So that path that we just wrote out. So you can write it out as well. You could be like H to E to B to A, D, C, B, F, D. So remember G, I, F, H, J, and I. So you can go back to the same vertex if you need to. You just can't cross the same path twice. All right, an Eulerian circuit. So remember, for an Eulerian circuit to exist, all of them have to have a even degree. So in this one, because of part A, we know that H and I had odd degrees. That means no, an Eulerian circuit's not possible for this particular network. Okay, let's go to part C, and I'm going to get rid of my scribbles now because for Hamiltonian we have to focus on the vertices. Let's do this one in blue. Hamiltonian path basically has to cover each vertex only once, and again we're going to use trial and error to figure out whether a path like this exists. And so you're basically going to see if we can cover each vertex only once. So I go from here to here, from here to here, did it. Oh, I'm stuck. If I go to J, that means I can't go back to E, so I can cover all of them except once. And you basically keep doing trial and error until we can do a pathway that crosses everything. And if we can't, well, then a Hamiltonian path does not exist. Okay, and then the last one, a Hamiltonian cycle, basically has to cover each vertex only once and return to the same starting vertex. So in this case as well, we actually cannot do it. It's going to be not possible either. That's just a trial and error. All right. Worked example number 9. So a salesman is traveling to 7 country towns to sell flour to the local bakeries. A map of the town is shown with the vertices representing the towns and edges representing the roads connecting the towns. The salesman wants to travel from town A to visit every town once on his journey and then return back to town A. So he wants to start at A and finish at A. What is this an example of? What kind of walk? So if he wants to go to every vertex, okay, once, and he wants to return to the same one that he started at, looking at our rules above, that is going to be a Hamiltonian cycle, okay? And then we could have to describe a route that this salesman would want to take. So looking at that, okay, if I start at A, again, trial and error. So let's go A to I, let's go to H, maybe G, let's go to F, E, maybe go this way to D, to C, to B, to A, and we did it. So that is the pathway. So I'd write those letters in order. And then list the edges that the salesman does not travel on. So he obviously doesn't travel on HF, so we could write that one down. GC is an edge that's not traveled on, and AC is also not traveled on, so we could include those. Okay, beautiful. Oh, I think there's one more. HF, GC, AC, and of course CE as well. That last one that I missed. Beautiful. All right, and the final example that we're going to basically go through is something called a weighted graph. So far I've just kind of shown you that, oh yeah, there's connections between these different towns. What we can actually do is give you information about maybe distances, times, or costs that can be labeled on each of those edges. So when extra information is required, it's going to show you like how this could maybe be applied in real life. A lot of the time it's distance. So an example could be the network shows the travel times in minutes along a series of roads that connect Chloe's home to Nick's home. Determine the shortest time that it takes Nick to travel to Chloe's house. So if we start at Nick's house and we want to get to Chloe, what's the shortest distance that we can take? So maybe we can do a pathway where we go from 8 to 10. Let's go the 5 because that's a pretty short number, and 12. And then we'd add up those numbers and we'd get 35. So that's the time that it could take to travel. If you have any questions regarding Eulerian and Hamilton's, just leave them below. Bye.